yesterday. And so this is what a lot of the test is going to be. So if you can do this and pretty feel good about life, you're okay. So, but let's talk about that assignment that I just gave back on that, and this whole concept of significant figures and all that stuff. So here's, again, your guiding light. Every calculation that you're going to do in this class is based upon something that you measured, okay? The final velocity of your car, how far an object falls, how long it's in the air, okay? The mass of Jupiter, whatever it is, okay? Every calculation in physics is based off something that is measured, okay? And there's a limit to how well we can measure things, okay? We saw that yesterday when Connor went out and ran, okay? Well, we kind of said, it ran about 10 meters, you know, we had a couple people time, and there was about 1/10 of a second difference between the two times, and it was like, okay, well, we'll take the average of the two times, okay? So that's the beauty of physics. Like literally every problem you are going to do, every problem on the test, on this sheet, whatever it is based upon a sequence. So basically what physicists do is they say, okay, we're trying to figure out what's happening in the way that we can describe mathematically what's happening in the world. So one of the equations that you've got is that for this pendulum, you have 2 pi times the square root of L over G. Okay, it's a cool equation, right? We randomly throw 2 pi in there. We throw 2 pi in there because it has to do with radians, and if you study about the unit circle, in 1 revolution there's 2 pi radians, okay? So that's the short version of that's where the 2 pi is incorporated into. So what we're saying is that, okay, we have this really cool equation. Okay, looks cool. So this is something that we can test. So if I build a pendulum of a known length, okay, and I know what G is, cool, I should be able to say the length, the period of that pendulum that it takes to go from here to here should be a certain amount of time. And then we can look at it and go, okay, hey, does that match the physical reality? When I build that pendulum, is that how long it actually takes? And if it matches it, the equation's valid. If it doesn't, we got to start over again, okay? So for those of you that have had Mrs. Fair for pre-calc, okay, you all did a pendulum lab, okay? I guarantee you all, it's a standard thing that you all did. And you're trying to take that data and you're trying to model it and go, okay, hey, is this what actually happens? You're trying to build a mathematical model. And that's what physics is searching for. Okay, that's it. It's like, how can we use equations to describe what's happening in the world? And then you get that equation, and then you, okay, well, what can we measure? Oh, okay, well, we can measure the length. Okay, well, how do we measure that length? Do we write it out as, you know, how long is it? Oh, it's about 1 meter, okay? Or do we say it's 0.857 meters, okay? There's a huge difference between those two. One situation you're going, how long is it? It's about 1 meter, okay? The other one is you have a very, very precise measurement. And so what determines that answer when you calculate T is based upon how good your data is that you put into it. So if you've got good data, I can get a good answer. If I don't have good data, I can only have an answer. And if you view those rules through that perspective, then that's what makes the difference. So if you look at when you add or subtract, okay, and so this is where you tend to struggle. So let's say we're going to add 8.75 to 2.3, okay? Maybe these were 2 lengths, okay? And those are the numbers that you have. So this is, if I see this data, here's what I'm going to think. Hector and Angel were measuring lengths, okay? And if I see this, so this is Hector's numbers and this is Angel's numbers, okay? So if I see these, I'm going to think these guys were using two different measuring devices. So if I see 2.3 meters, what I'm going to think is that Angel has a meter stick, and it's a horrible meter stick. Basically, Angel has a meter stick that only he has 0 and 1. Okay, that's it. He has a meter stick that's marked off at 0 and 1. There is nothing in between. That's it. He has 0 and 1. Crappy meter stick, okay? But really, really cheap on Amazon, okay? Why is it on sale so cheap? Because it doesn't have any marks on it. Because if I see 2.3, what I think is that he knew that that distance is somewhere between 2 and 3 meters, and the best that he could do was estimate the tenths. That's it. So when I see that measurement, that's what I think in my mind. His meter stick has a mark at 0, and he has a mark at 1, and he can only estimate the tenths. Now, Angel's is a little bit better. His is 8.75. Okay, so what that tells me is he has tenths marked off on his meter stick, and now he can estimate somewhere in between 0.7 and 0.8. So he's going to know the 7, okay, this is going to be a known value, and he's going to estimate that one, okay? So we're going to add these two numbers together. Angel's is to the 10th, Hector's is to the 100th. But here's what's going to happen. My answer can only be as precise as the least precise place value. And since Angel's is only good to the 10th place, that means I can only write my answer to the 10th place. So you plug this into your calculator, and your Oracle speaks to you, and it says it's 10.05. That's what your calculator says the answer is, okay? 10.05. Now here's the problem. If I write down 10.05, I'm going to think that both of their measurements were to the same place value. Okay, that's what I'm going to think if I see that number. And that's the mindset that you have to get into. This door swings both ways. When you look at the data, set of data, you can figure out the measurement, how precise was that measurement, but then you can also reverse it. Oh, here's my measuring device. How many decimal places can I have? So the door has to swing both ways. So if I see 10.05, I'm going to think Hector and Angel's measurements were to the exact same degree of precision. They weren't. Angel's is only good to the nearest tenth, okay? So therefore, I can only write my answer to the nearest tenth. And since that's the 5, I've got to write that as 10.1. So that's how I have to write that answer. So when you're adding or subtracting, the number of significant digits isn't a factor. The only thing you look at is place value. And when in doubt, stack these numbers. Line them up all in line with the same decimal place. And you find that place value that is the least precise, and when you write that answer, that's what you're going to round that to. Okay? Now, let me give you this statement. True or false? Okay, so listen very carefully to what I'm going to tell you. True or false? You're comparing two different measurements. Okay? Two different measurements. True or false? The measurement that has the most significant figures is also the one that is the most precise. Okay? So let me say this again. I'm comparing two different measurements. The one that has the most significant digits is also the one that is most precise. Now, Adana, you shook your head no early on that. Why?
Because just because it has a lot of significant digits doesn't mean it necessarily has decimal places.
Ah, beautiful answer. Okay, so let's look at two situations. So let's look at two different measurements. 552,500 meters. Okay, no decimal place. 52,500 meters. And then I've got 1.2 meters. Okay? So I have 52,500. There's not a decimal place. So Peyton, How many significant digits are there in 52,500?
3.
Yeah, so this has 3 significant digits, okay? 1.2, how many significant digits? 2. So this has 2 significant digits, that has 3 significant digits. Which one's the most precise measurement, though? The 1.2. So just because a number has more significant digits doesn't mean that that's the one that's most precise, okay? Because your precision is going to be determined by the number of digits to the right of the decimal place or the number of divisions on the measuring device, okay? It's cool. All right, now, when you multiply or divide, and I promise you, okay, I promise you on the test tomorrow, okay, or on Tuesday, okay, I promise you on the test on Tuesday, I'm going to give you 2 different problems that you're going to have to work. One when you add or subtract, and one when you multiply or divide. It's going to be on the back side of the test, okay? I'm going to tell you exactly where it's going to be. It's on the back side of the test, about 2/3 of the way down on the bottom side, okay? I'm going to tell you where the problem is going to be. So the first, I'm going to give you something like this. I'm going to say, hey, 8.75 plus 2.3. That's going to be one of them, okay? The other one I'm going to give you is you're going to say, okay, let's take 5.28 meters per second, and I'm going to divide that by 0.012 seconds. Okay? So, because I'm dividing, and this, what determines how you're going to write your answer? The number of significant digits or the least precise place value? Jack?
Dividing is the number of significant digits.
Fantastic. So you have 5.280 meters per second. How many significant digits are there? Tyler, how many significant digits are there? 5.280.
4.
Beautiful. Why? Why do I count that 0 on the end? It's a freshman. Why does it count?
Because it was measured first.
Use the word precision. Let me ask you this, Tyler. Is 5.28 the same as 5.280? In other words, if that 0 wasn't there, would that convey the same information as that 0 being there?
No.
No. Because what do you know about the last digit in the measurement? Is it known or is it a guess? The last digit, is it a known value or is it a guess?
I guess.
It's a guess. So here's the difference. If I have 5.28 without the 0, that tells me I know the 5, I know the tenths, and I'm estimating the hundredths. If I put the 0 on the end, that tells me I know the tenths, the hundredths, and then I'm guessing the thousands. So that 0 is there, and it's important because it shows the precision of the measurement. Okay? So that's why this has 4 significant digits. Now, this 0 here, just taking up space. This is the quintessential freshman. It's just taking up space, and it's not important. And here's the reason why. So if I took this number and I put it in scientific notation, if I put that in scientific notation, I would have 1.2 times 10 to the minus second, which is only going to have 2 significant digits. So here's the deal. If there's a decimal place, you count right. So I'm going to start here. I'm going to count right. I have 1, 2, 3, 4 significant digits. There's a decimal place here, right? I hit the first non-zero digit, and then I start to count. So these zeros here don't count. I hit the first non-zero digit, and then I start to count. So this just has 2 significant digits. Okay. So my answer then can only have two significant digits, right? So here's the deal. Punch this into your calculator and let me know what the oracle says the answer is. So somebody take 5.28 and divide it by 0.012. What does the oracle say the answer is?
440.
Exactly?
Yeah.
Exactly 440?
Yes.
Seriously?
Yeah.
Okay, that was completely random. It wasn't supposed to work out that nice. Okay, let's go with it though. All right, so if I put I'm going to give you some options. Option number 1, I put the answer is 440. Option 2, I put 440 with a decimal place. Option 3, I put 440, and then I put a decimal place on the end. Do all 3 of those measurements convey the same amount of significant digits? Izzy, do all 3 of those measurements have the same number of significant digits?
Yeah. Well, there's not like a number besides 0 on the right, so I want to say no, but I also want to say yes.
I want you to say no.
Okay.
As your physics teacher, I want you to say no. Okay? So here's the difference. This says, it's about 440. It's a ballpark. How fast? It's about 440. Okay? This, because there's a decimal place, now here's the deal. If there's a decimal place versus not a decimal place, this is what you have to get straight. If there's not a decimal place, you count left. So there's no decimal place here. So I find the first non-zero digit, I count everything to the left. So this just has 2 significant digits. If there is a decimal place, you count to the right. So this is going to have 3 significant digits. This one's going to have 4 significant digits. So even though they're both 440, they convey completely different degrees of precision. This has 2, this is a ballpark. It's about 440. This, 440, okay? More precision. So we're saying, hey, I put that decimal place there. What I'm saying is that this 0 is a freshman, but it's a cool freshman. This one says, 440.0. This conveys a very high degree of precision because I'm saying, hey, I'm estimating the 10th place. So mathematically, the 3 numbers are the same, but they convey completely different degrees of precision. So I do this calculation. How am I going to write my answer? Which one of these is going to be the right way to write my answer? Top one, the middle one, or the bottom one? Miss Elliott.
The top one.
Top one, because I can only have 2 significant digits. Okay? Now, am I done? Can I walk away from this problem at this point? Adonna, thank God you shake your head no. Why? What do I not have?
Units.
I don't have units. I have 440. Is it squirrels? Is it Oreos? Is it freshmen? What do I have? Okay? I got nothing. I have 440. This is not a math class. Okay? This is a physics class. So we have to put units on the end. So I took meters per second divided by seconds. So here's your 2 options. So did the seconds cancel out and I get meters? Or do I take meters per second, multiply by the reciprocal of seconds, and get meters per second squared? So do I get a distance of meters, or do I get an acceleration in meters per second squared? Jaden, which one do I get?
Acceleration.
You say that with absolutely no confidence whatsoever. You're right. Okay, you do get acceleration. Okay? And this is the most common mistake that's made. This is the most common mistake that's made. You all see this. You see meters per second divided by seconds. You think the seconds cancel. And I saw this on the homework assignment that I just gave back. The one you all did on dimensional analysis. And I told you all, this is what you're going to do. You're going to see meters per second divided by seconds. You're going to cancel that out, and you're going to get meters. And you all said, oh, Mr. Burkamp, we won't do that. I said, you lie? You lie. And sure enough, about a third of you ended up with meters. Okay? And even though you told me you wouldn't do that, guess what you did? You did that. So here's the story. Okay? And here's the difference. If I multiply meters per second by seconds, the seconds cancel out and I get distance. So this is like saying Jaden ran 5 meters per second for 2 seconds. Oh, she ran 2 meters, or she ran 10 meters, okay? So a velocity multiplied by a time gets you a distance, okay? But a velocity divided by time gets you an acceleration, okay? So that's what you have to keep straight. And again, you all sit there and go, Mr. Burkamp, on the test, we won't make that mistake. We promise. You lie. You all lie. Not all of you, but some of you lie. Okay. All right. So you got that idea. All right. So let's chit chat. Let's go now. With all that said, let's go back to this assignment. So when you get to, let's start with 9 and 10. Okay. Let's start with 9 and 10. And I promise you, on the test on Tuesday, you're going to have one like 9 and 10. I absolutely promise you. It's going to be on the back side of the test, about halfway down. Okay? That's where it's going to be on the test. Okay? So let me give you all a hint. When I tell you something's going to be on the test, I'm not lying. Okay? It isn't like I show up on Tuesday morning and the tests are on my desk and I look at the test and I think, wow, I didn't teach the kids that. Man, I feel bad. I'm going to ask them questions on the test that I didn't prepare them for. Okay? I write the tests. Okay? I know what's going to be on the test. When I tell you this is going to be on the test, trust me, that's what's going to be on the test. So here's what's happening on number 9. So here's our star that we've called the sun, okay? And in the Greek they call it Helios. And here's this strange rock that we're on, okay? And it relative to the other planets, we're a strange rock, okay? We're the only one that has like liquid water and a nice atmosphere and everything, okay? If you ever get the chance, there's a great series. It's hosted by Will Smith, and that's the name of it. It's called One Strange Rock, okay? It does a great job of kind of going through like the history of the Earth and that. So if you ever get bored and you ever find that, you can stream it, okay? It's called Strange Rock. It's a great series. It does a lot of like astronomy and geology, biology. It's a really cool series. Okay, so here's our rock, and we're trying to get an idea of how fast this thing is moving, okay? Now, and on the test, I'm going to give you this equation, okay? I'm going to give this to you. It's going to be there. You just have to know what to do with it. And again, don't flip out and go, oh, that's hard. That's pies and all this other stuff. All this is, literally, is distance divided by time, okay? That's it. All I'm saying is like I'm taking this rubber stopper and I'm swinging it around over my head. And I'm trying to figure out how fast it's going, okay? And if you take the Earth as it's going around the sun, it's the exact same idea. It's just on a bigger scale. So don't flip out on this equation and go, oh, man, that's tough. 2 pi r just gets you circumference. Period tells you how long it takes for it to go around, okay? So don't flip out and go, oh, that's tough. It's distance divided by time. That's all it is, okay? So you're going to take 2 pi and pay attention to this radius, okay? So that's 1.50 times 10 to the 8th kilometers, okay? And then you're going to divide that by 365 days. But we can't have days, so we go 1 day is 24 hours. Okay? So That's all you have to do. Promise you, promise you, promise you. On the test tomorrow, if you don't do something like this, if you hand in that test and go, oh, man, I didn't take kilometers and divide it by time to get a velocity, you have done something horribly wrong. Okay? It's one of the things you're going to do, I promise you. Okay? And I'm not going to make you do anything funky. I'm just going to say, hey, calculate the velocity. That's all you have to do. Now, the next thing you want to do is you want to take that and change that into meters per second. So pay attention to the units. This is kilometers and this is divided, this is hours, right? So what does somebody get for that answer? On number 9, what did you get for your answer in kilometers per hour? Now, here's the story. I want your answer in scientific notation with 3 significant digits, okay? And that's how many I should have because 1.50 only has 3 significant digits. Therefore, my answer can only have 3 significant digits. So what did somebody get from that first answer on number 9? In scientific notation with 3 significant digits.
1.08 multiplied by 10 to the 5th.
Times 10 to the 5th?
Kilometer or something.
Beautiful. Anybody else get that? Everybody cool with that? Okay, fantastic. That's what you should get. Okay, spot on. Well done. Okay, there you go. 3 significant digits, 1.08 times 10 to the 5th. So that's the first calculation you're going to do on the test on Tuesday. Is something like this. Okay. Now the next thing I want you to do is change that into meters per second. So what I would recommend is that you take this. Do not make this difficult. You don't have to start over from scratch. Just take this. Okay, and that's how many kilometers you're going to go in 1 hour. Okay, so it's a pretty big distance. So now we need to change that into meters per second, and it works the same way every time. Come down here and put 1 kilometer, put 1,000 meters up there, put 1 hour here, and 3,600 seconds down here. Literally, it is the same thing every time. The only thing that you change is the number that goes up here, okay? Everything else is the same every time, okay? The only thing you change is how many kilometers you go per hour. That's it. That's the only thing that you change. So your kilometers will cancel out, your hours will cancel out, you get meters per second. So the shortcut is that you multiply by 10 and you divide by 36. Okay? That's it. Multiply by 10, divide by 36. So when you do that, so Hector, what did you get when you did that? So 3 significant digits, scientific notation. What did you get?
3.00 multiplied by 10 to the 4th.
Times 10 to the 4th?
Yeah, meters per second.
Meters per second. Okay? Cool. Now, here's the deal. When you convert from kilometers per hour into meters per second, and you're going to do this a lot, okay, it's the most common conversion you would do in this class. Here's what's important. When you get this answer here, your answer has to be less than numerically than what you started with, because you're multiplying by 10 and you're dividing by 36. So when you get this answer, go back and look. Ask yourself, wow, is this smaller than what I started with? If it is, at least you have a fighting chance that you did it right. If you do this conversion and that answer is bigger, you have done something horribly wrong. Okay? So every time you convert from kilometers per hour into meters per second, you have to end up with an answer that is numerically smaller than what you started with. Okay? Cool with that. All right. Now, let's talk about number 10. So number 10, our strange rock is spinning. Okay? And it's actually slowed down quite a bit from when we think the Earth was first formed. We think a day was about 12 hours, okay, instead of 24. So the Earth is actually, and it's still slowing down a little bit, okay? It's just like anything. Like if I spin my Gatorade bottle oh, it slows down. Okay, the same thing is true of Earth. Earth is slowing down as it's spinning. Okay, not a lot. Okay, so when you look at what's going to happen on this one, so like here's Al, right? And he's here, and he's going to go around on this strange rock. Okay, and we're going to figure out, hey, how fast are you going as this Earth spins? So you're going to do the exact same thing. You're going to start with 2 pi r over t. Now, what did you use for the t on number 10? 365 days or 24 hours? 24 hours, okay? So, what did somebody, just as your exponent, what did you get for your exponent on the kilometers per hour? 10 to the what? 10 to the third, okay? So that's what you should get, okay? So that's going to be like 10 to the third. Now, on your answer to meters per second, you should get an answer, and this is an ish, of about 400 meters per second, okay? It's an ish, but it's something around there. So here's where this created a problem. This number was very problematic because if you go back historically, and one of the debates is the Earth stationary and the sun moves around us, or is the sun stationary and we're just spinning, okay, as we go around? That was a huge debate. And so one of the things that they began to look at is like, okay, let's assume that the Earth is spinning. So we've actually known the radius of the Earth since antiquity. Okay, and you're sitting there going, well, how could you measure the radius of the Earth? I mean, that's a tough gig, you know, especially when that was before you had space travel and anything else. So it isn't like we could go outside the Earth and take a selfie and go, hi, and then work backwards and find the radius of the Earth. So it was clever how they did it. And this is a short version of a very long story. But they knew on a certain day there was a tower. This is like in Egypt. On a certain day of the year, when the sun shone on this particular tower, there was no shadow. Okay, so if you've ever been outside, okay, during the day, and the sun is shining, you look, you cast a shadow. Okay? And even on a full moon, okay, if it's a really bright moon, you will cast a shadow from moonlight. So, what they observed is that on a particular day of the year, this particular tower did not cast a shadow. Okay? There was absolutely no shadow on this thing. They knew at another location where there was a tower that it cast a shadow. Okay? Same day. This tower did not cast a shadow. This tower did. So they assumed that those rays of light were coming in parallel with each other. And they knew how far apart these towers were. And so basically what they did is they worked out the geometry, and they said, okay, well, if they knew this angle and they knew that distance, this was like part of the arc length of the circle. And then they extrapolated that out and said, well, if this is the degrees and this is the arc length, then we can work out the circumference of the Earth. And then once you knew the circumference of the Earth, then you could figure out the radius of the Earth. Okay, so it was a clever way they did it. And they were actually off by some because they were off on the distance between the two towers, but they were actually relatively close. So we've known the radius of the Earth since antiquity. So then they started doing the math. They said, oh, okay, cool. All right, let's do the math. And here was the problem with 400 meters per second. The problem with that is that, for example, the speed of sound is about 333 meters per second. So if this is true and the Earth is spinning on its axis, you're going faster than the speed of sound right now. Okay? And that's problematic for a couple of reasons. First off, let's go back to your youth. Anybody ever ride their bicycle like through a puddle of water? Anybody ever do that? Okay, Jade, you rebel, you. Okay, you rode your bike through a puddle of water. What did that water do Did it stay on the tire or did it go flying off? It flew off, right? Okay, it's cool, right? Okay, water flying off. Okay, it didn't stay on the tire, it goes flying off. You ever seen a car driving in the rain? You see water flying off the tires all the time, right? Well, that tire without water, let's say it's going 20 meters per second, okay? And that's fast. Let's say it's 20 meters per second. Well, even at 20 meters per second, the water goes flying off, okay? So if here's a tire, water flies off at 20 meters per second. If the Earth is spinning at about 400 meters per second, why doesn't the water all go flying off? Now, that was a legitimate concern, is that we're going faster than the speed of sound. It's a really high velocity, 400 meters per second. Why do we have oceans? Why, if the Earth is spinning this fast, and if the water goes flying off your bicycle tire at 20 meters per second, why doesn't water go flying off the Earth if we're moving at 400 meters per second? That was a concern. It was like, how can we have oceans? That was one of the arguments against a spinning Earth. It was that, this is problematic. We're going really fast, and we still have oceans. How does that happen? So what's your answer? How do you explain it? We obviously have oceans. We have water. We have even Cheney Lake, which isn't an ocean, but we have water. Okay. So what's the explanation? What do we have that the tire doesn't?
Gravity.
We have a lot of gravity. Okay, we have a lot of gravity because we have a really, really, really big mass of rock that we're on. So later on, you'll do that calculation, and you'll see that gravity provides more than enough force to hold that water on. Now, the Earth is actually a little bit non-technical. It's a little bulgy. Okay, the Earth is actually flatter on the poles than it is in the middle. So the Earth is actually like squatted out in the middle because we are spinning. So it's spinning like this and it's going out like that. Now here's the other problem with this. So let me ask you this. We have an atmosphere, okay, which is a cool thing, okay? So like on a relative scale, if this was an apple, okay, and you cut that apple in half, if this was the size of the Earth, our atmosphere is that thin peel around the outside. That's the only thing that keeps us from dying in space, is that layer. So here's the question. We've established that the Earth is spinning. So here's the next question. Is our atmosphere moving with us, or is the air stationary and the Earth is spinning through the atmosphere? Okay, so that's the question. Does our atmosphere move with us, or is the air stationary and we move through the atmosphere? Two options. What do you think? Yes, Nathan.
The atmosphere moves with us
Why?
because it'll be very windy if it doesn't.
It's a brilliant answer. Okay, spot on answer. So, again, go back to your misspent youths. Okay? Guessing mom, dad, somebody at some point had a minivan, okay, or a car, right? And this is back when you maybe didn't have phones and you were completely glued to your phone, staring at TikTok videos and wasting your life away. And God forbid that you might have even actually experienced nature, okay? And you're going, really? There's nature? And let's say that you actually took the time and you lived on the edge and you rolled the window down on the minivan. Okay, so you put down the electronic device. Visualize this. You set down the electronic device, you roll the window down, and you stuck your hand out the car window. Anybody ever do that? Cool. Okay. Did you ever do this one when you're cool and you're like riding the wave? Okay. All right. If you've never done that, if you've never done that, it's your homework assignment for today. On the way home, roll down the window, go. So now that's going about, say, 40 miles per hour. You stick your hand out there, okay, right? So 40 miles per hour is about 20 meters per second, roughly, okay? And you feel that, right? So if our atmosphere was stationary and we're moving at 400 meters per second, okay, What that means is that when we should be exactly what Nathan said. It would be really, 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 really windy, okay? As soon as you step out of the building, okay, boom, right? You just get knocked down. Birds, boom, okay, trees, boom, okay? Always laid over. So our atmosphere moves with us. Now, sometimes we get wind, especially here in Kansas, right? So wind is occurring because of a pressure differential between a high pressure system and a low pressure system, okay? So, but it's cool, though our atmosphere is moving with us. So that was one of the big debates, is that what does the atmosphere do? Well, the atmosphere moves with us, or if it wasn't, it's just exactly what you said. It'd be really, really windy. Okay, so let's talk about number 11. On number 11, I promise you, you're going to have one like number 11 on the test. Okay, it's the only graph you're going to have to draw. I'm going to give you a half sheet of graph paper, and you're going to figure out where you're going to put this. So here's the question. I'm going to give you force, and I'm going to give you acceleration. Which goes on which axis? Force goes where?
X-axis.
Why?
Because it's what you're controlling.
That's what you're controlling, okay? You're controlling how hard you push the rubber stopper. Do you give it a little bit of push? Do you give it a lot of push? Okay, you control that. You have acceleration here. Is this graph going to start at 0, 0? Yes, why?
No force, no acceleration.
No force, no acceleration. Mother Nature is a lazy prima donna. Mother Nature is not going to make that rubber stopper accelerate until I apply a force to it, because Mother Nature is going, we're chill, it's cool, right? I can sit here, hit my hookah pipe, and just chill out. You want the stopper to move, you move the stopper. I'm not touching it, okay? So it's going to go something like this, right? So you've got your force, you have your acceleration, boom, there you go, okay? Pay attention to the units. So on that first one, I want the slope of the line with the correct units. So let's say, for example, you picked that first one where you have 5 newtons and 1 meter per second squared, okay? Now, in a math class, if you pick that point and use 0, 0 as the other one, which is cool, in your math class, you would say the slope is 1/5. Okay? In a math class, that's what you would put. Rise over run, 1/5. That's what you would put. And you would get full credit for your answer. Okay? Now, if you put 1/5 as your slope, you all now have known me for a while. How happy am I going to be if you put a slope of 1/5? Oh, bad things going to happen. My blood pressure is going to go so high, it's just going to be horrible, okay? Physics teacher dies of stroke, blames physics students for putting fraction as a slope, okay? Y'all don't want to live with that burden, okay? So, technically it's right, but mathematically, in a physics perspective, it's horrible. So what should you do? Change it to a decimal. Now, let's say that you put 0.2 as your slope. How's that going to work for me? A little bit better, okay? At least I'm not going to have, a stroke right when I see 1/5, right? Still not going to be good. How many significant digits are in every data point that I gave you? 3. Every one of those has 3 significant digits, okay? So how many significant digits should your answer have? 3. If you put 0.2, how many is that? 1. So what are you going to do? Yeah, chuck some zeros on the end of that. Okay, now I have 3 significant digits. That's cool. I gave you good data, okay? I took a lot of time typing zeros in here. Don't cheat me on my zeros, okay? Throw some freshmen on the end. They're cool in this situation. So I have 0.200. Am I happy at this point?
No.
Oh, I'm still not happy. Why?
Units.
I don't have any units. Okay, I don't know what this represents. 0.2 what? Squirrels, earths, black holes. I don't know what it means. So, you could put meters per second squared per newton. Okay, you can do that. works, kind of a lazy way out. It's not horrible. At least you put something down, you tried. Okay, here's a participation ribbon. But is that really what I want? No. I want meters per second squared. Now, what's the other way that you can express newtons? Kilograms, meters per second squared. Now you're talking my love language, right? Now we're talking. So this is going to cancel out and you get what units? Do I get kilograms or do I get 1 over? Because there's a huge difference. I get 1 over kilograms. So depending upon how cool you want to be, you could put 1 over kilograms or you could put kg to the minus 1. Okay? So that's how you know to answer B when it says what physical quantity is shown by the slope. Because here's the difference. If you think you get kilograms, you would say the slope would represent mass. But because you get 1 over kilograms, the slope represents the inverse of mass. Okay, and that's the difference. Okay. Now, on D, how much force would be needed to produce an acceleration of 6.5 meters per second squared? So on C, let's back up a little bit. I asked you to write the general equation for the line. So this is linear. It's y equals mx plus b. Am I going to have to worry about the y-intercept? Why? Yeah, 0. Graph starts at 0, 0, no force, no acceleration, right? So what's graphed on the y-axis? Acceleration. So I'm going to put A equals, and then you're going to have your slope times your force. So this is what I'm looking for on C. This is what I'm going to expect on the test on Tuesday. Okay? Something like this. If you hand in that test and you haven't written a linear function that looks like that, you have done something horribly wrong. Okay? Now, I want to know how much force would be needed to produce an acceleration of 6.5 meters per second squared. Now, look at your data. Step back. Don't even try anything on D, okay, in terms of an equation. Look at your data, okay? You want an acceleration of 6.5 meters per second squared. What does your answer for force have to be bigger than? 30. Okay? It has to be big because a force of 30 newtons produces an acceleration of 6 meters per second squared. So if I want an acceleration of 6.5, right away I know my answer, when I get done, my answer has to be bigger than 30. If I don't get an answer bigger than 30, I've done something wrong. Okay, so basically come in here, here's your acceleration, boom, you got that number, divide that, there you go. And again, this is where the magic happens in terms of the process. You've got meters per second squared divided by 1 over kilograms. The kilograms flip up, I get kilograms meters per second squared. That's what force is measured in. Okay? Promise you, you're going to have to do something like that. Promise you. Okay? Now, when you get to number 12, okay, so let's talk about number 12. So what's happening on number 12 is we're saying, here's this strange rock that we're on, and we're going to shine this beam of light, and it's going to go around the Earth, which would be cool. Okay, it doesn't, because light travels in a straight line, because it's also lazy. And you want to figure out on A how long it's going to take. So you're basically going to start with this idea that the velocity equals 2 pi r over t. Okay, that's it. All we're saying is that we're going to make this beam of light travel around the circumference of the Earth, so we know enough to figure this out. We know how fast it's going. Speed of light, 3.00 times 10 to the 8th meters per second. And I want to get time by itself. Okay? So this is what I would recommend. Solve the equation first. Okay? So T for Tyler. How am I going to get T by itself? What would you do? I want to isolate T as a variable. What would you do?
Multiply it over first.
Fantastic. So I'd have VT equals 2 pi r, then what?
Divide by V.
Divide by v. To v or not to v? Let's divide by v. Okay? So this is, if I were working this problem, this is the first thing I would do. I'd do the algebra first, and then I'd put in the numbers. Now, what I'm going to do is wrong. Do not do what I'm about to do. It's wrong. Do not do what I'm about to do. So I'm going to go, okay, 2 pi, let me see, there's a radius, 6.37 times 10 to the third, velocity of the speed of light, 3.00 times 10 to the 8th. And then I'm going to punch those numbers into my calculator. Okay? Why is this so horribly wrong? Units. Here's the deal. Let's say I put those in, and let's say I put that in. So here's the problem. I have kilometers here, I have meters per second there. Could I take kilometers and divide that by meters? Can't do it. Can't do it. So you have to make a decision. Do you want to change this into meters by multiplying by 1,000? Or do you want to change this into kilometers per second by dividing by 1,000? I don't care which one you do. Okay, it makes me no difference. If it were me, I'd multiply it by 1,000. Then this becomes times 10 to the 6th. Okay, that's what I would do. That's just me, though. I like meters. So here's what's going to be important, though, in terms of dimensional analysis. I have meters divided by meters per second. So when I do that, and take meters and divide that by meters per second, that's like taking meters times seconds over meters. The meters cancel out, I get seconds, that's what period's measured in. Okay? So what you should see on that answer to A is around 0.1 something. Okay? So that's what you should have as your answer of A, 0.1 something. So what that means is that if you're here on the Earth at the equator and you turn on a flashlight, that light would travel all the way around the Earth and come back to you in less time than it takes for you to snap your fingers. Okay? That's how incredibly fast the speed of light is, which we've also figured out is also the speed of gravity. Okay? Gravity and light travel at the same speed of 3.00 times 10 to the 8th meters per second. Now, so that's what you're going to have as your answer to A. So on B, you want to find in 1 second how many times can the beam of light travel around the Earth. So on your equation sheet, you have this relationship between period and frequency. They're inverses of each other. So let me kind of give you a visual on them. So here I've got this rubber stopper, and I'm moving it pretty slowly, okay? So that means if I'm moving slowly, it's going to have a long period. It's going to take a long time for that rubber stopper to go around because it's going very slowly, okay? But you're not going to see the rubber stopper go past you very often. So, in other words, if I said, hey, how often does that rubber stopper go by? Not very often, okay? Because it's taking a long time to go around, so you're not going to see the rubber stopper go past you very often. Now, if I speed it up like this, okay, now the period has become a lot less, okay? It doesn't take very long for it to go around. But now, because it's going so fast, you'd see that rubber stopper go past you a lot more often. Okay, so this is why these are inverses of each other. So, what you have is period. That's what you found on your answer to A. Okay? Just like if you're talking about that rubber stopper going around, hey, how long does it take? So if I were to get frequency, if I solve for frequency, do the Tyler thing, and multiply and then divide back. So frequency is the inverse of period. So to get your answer to B, that frequency, you're going to take 1 over 0.1, whatever it is, as your answer to A. So to get B, you're going to take the inverse of your answer to A. Now, here's where the magic happens. that period technically is seconds per revolution. Okay, technically those are the units. It's seconds per revolution. So what happens is that when you take the inverse of that, you have 1 over seconds per revolution. The revolutions flip up. You get revolutions per second. That's what frequency is measured in. Okay, so that's the other reason why they work out to be inverses of each other, is just to make the units work out. Okay, so your answer to 12B should be around 8. Okay, it's an ish, but it should be something around 8. So what that means, physically what that would mean, is that if you could turn on that beam of light and you could make it go around in a circle, what that would mean is if you could sit there and count, you would see that beam of light pass you about 8 times per second. So if you consider a second, 1001, that's about 1 second right there. You would see that beam of light pass you 8 times. You couldn't even count to 8. What are they for 5, 6, 7, 8? Okay, it would be a challenge to count to 8 in 1 second. That's how many times that beam of light would come around and pass you. That I put that on there so you get an idea just how fast light really is. Okay, when you get to number 13, I promise you you're going to have a question like number 13. Okay, and on the test I'm going to say, hey, here's an equation. What's going to happen if you do something? So you have V equals 2 pi r over t. And I want to say, okay, what's going to happen if the radius is constant and we double the period? Okay? So there's 2 ways you can do this. You can do this on the test. I don't care what you want to do. One option is that you do smash mouth physics. You come in here and you say, okay, hey, I'm going to let the radius be 1 meter. It's a simple number. So you got 2 pi times 1 meter. And an easy period to use would be 1 second. So if you like smash mouth physics, take 2 pi times 1 meter, divide that by 1 second. Oddly enough, you get 2 pi. Okay? That's your answer, 2 pi. Now, what's going to happen is that we're going to double the period. In other words, it's going to take twice as long for this thing to go around. So let me give you that visual. Okay? So this thing is going around like this. Okay? Right? It has a certain velocity. And then I'm going to slow it down where it takes twice as long to go around. So what happened to the velocity of that stopper? Increase or decrease? Decrease, right? Took longer, right? Because it's going slower. So if you like smash mouth physics, then you'd come in here and you'd redo that calculation and you would put in 2 seconds. Okay? And then you'd see that cancels out. So basically I'm going to go from 2 pi to pi. The time is going to be half as much. Now, if you want the more elegant approach, go 2 pi r over t. That's your initial velocity. Then the new velocity is going to be 2 pi r over 2t. I'm going to divide by t. The velocity would be half as much because I'm dividing it by 2. I don't care how you think through it. Okay, it makes me no difference at all. You can do smash mouth physics. You can go with the elegant approach. I don't care. Just figure it out in terms of your thought process and what you feel most comfortable with. Okay, let's talk about on number 7 on that, on B, where you have V squared equals V naught squared plus 2AD. So this is an equation we will use a lot. Okay, this is going to be one of our go-to equations eventually when we get into kinematic and stuff. Okay? So, with this one, hello?
Hello, really quick question. Us kids are working on empirical formulas. I know there's a saying. It's mass to moles divided by small, multiply, tell, whole, and there's one more line.
I've never heard that before in my entire life.
There's a whole saying. Robbie says it, so does Angie. I did for years, and I just can't remember the last line today. So, okay, here you go. Bye.
Sorry. Okay. Okay, so I know how to do the math. I just don't have the cute little saying. Okay, so this is what's known as that equation. Okay, literally, when we start talking about this is going to be that equation. This is the only one that's called that equation. Okay, and so what I'm asking you to do is solve this equation for acceleration. Okay. So no. So I'm talking it's number 6. The 6 is the one I want to do. 6 is the one I want to do because you want to solve it for V0. So you're going to come over here and you're going to go, oh, V squared minus 2AD equals V0 squared. Okay, and then you're going to take the square root of both sides, right? So I'm going to have V squared minus 2AD equals V0. Now, here's what some of you are probably I'm guessing some of you have done. You looked at that and you said, oh, the square root of V squared is V. I'll take V minus the square root of 2AB. Anybody have that? Can't do it. Bad, stop, no, horrible, can't do it. Okay, can't do it, can't do it. This is as far as you can go, okay? And here's the reason why. If they were multiplied together, you could do that, okay? You could do that. But it's not multiplied together. It's all underneath one radical. And here's the reason why logically. Because, like, what's the square root of 4?
2.
Or -2, right? Anytime you take the square root, it's a positive or negative value. So if you try and do this, then you don't know whether to have the positive or negative value of this, and then you don't know whether to have the positive or negative value of this, and then you have like 4 possible permutations. You could have positive, positive, negative, negative, positive, negative, negative, positive, and you would actually have 4 potential answers out of that calculation. Okay? So it's a train wreck that way. That's why you keep it all underneath the radical. Okay? So on a problem like this, and I promise you, you are going to solve this equation a lot for V0. You're going to figure out how fast the airplane was going so that you knew how fast it was going later on with a certain acceleration. So when you do this, do not separate that out and take that down to that next level. Okay? Cool with that. I've pretty much gone through everything. Is there any specific things you want me to go over? You can, by the way, with this assignment, you can hand it in on Tuesday, or you can hand it in if you want to keep it over the weekend to study, because this is what a lot of the test is going to be. If you want to hold on to it, you can, and then hand it in on Tuesday. If you're done with it and you feel good about it, you can hand it in. Doesn't make any difference. But does anybody have any questions at all on any of these? You say, a little sketchy on this one. Or is everybody good on everything? Everybody good? Okay. Stand up, take a stretch. I got my copier jammed this morning, so I had to go print to another copy. Or I need to go get the topics that you all need to know for the test. So let me run and get those right quick. I'll be right back. I hate copiers. Okay, one other thing on that assignment where you have the one with the pendulum, where you have t equals 2 pi square root of L over g. So if all goes well on that answer on B, on 8B for the length, that should be around between 0.5, somewhere between 0.5 and 1. Okay? So that's about where that answer should fall. It should be somewhere between 0.5 and 1. When you get to D and you want to find the gravitational acceleration of the planet Zoltar, randomly made that one up, that answer should be between 3.5 and 4 meters per second squared. So that was actually one of the things that they did when they went to the moon on the Apollo 11 missions. And what they wanted to figure out was, hey, what is the gravitational acceleration on the moon? So literally, one of the first experiments they did when they landed on the moon is they set up a pendulum, and they measured the length, and they measured the period, and then they figured out little g on the moon. And then later on, you'll see how you do this calculation. But once you know what little g is, then you can find the mass of the moon or the mass of the earth or whatever that is. And so it was kind of cool. We actually landed on the moon and we didn't know what the mass of the moon was. We had a vague idea, but we didn't know the exact value until we actually landed on the moon. Okay, so here's what's going to be on the test. Okay, so let me kind of go through these. MKS system. So on the test, the first probably 8 or 10 questions are going to be multiple choice questions, general knowledge. Okay, what are the units for velocity? What are the units for acceleration? Okay. I might ask you, if I multiplied velocity by time, what units would I get? What would happen if I multiplied velocity by, or acceleration by time? What would I get? What would happen if I multiplied acceleration by time squared? So, let me give you a hint about how I would prepare for this test. You have back every assignment that you have handed in. Okay, you have them all back, and if there's wrong, if anything's wrong, I corrected it. Go back, especially like, let's say for example, you talk about dimensional analysis. A little sketchy on that. We did an entire assignment on dimensional analysis. Go back, cover up your answers, and start over from scratch. Okay, and just say, hey, I'm going to cover this up. Boom. I'm just going to see what I get. You know there's going to be questions on calculations involving significant figures. I just gave you back that assignment, okay? If there's any that you missed, figure out what you did wrong. And then you work those problems again and again and again. So here's the best analogy that I can get. Let's say that you're a tennis player, okay? Basketball player, whatever, okay? You're going to get good at a sport. You have to practice again and again and again and again and again and again and again. Kobe Bryant, one of the greatest basketball players in the world, he would go in before games, like an hour before the game, and he would just shoot and shoot and shoot and shoot and shoot. Physics is the same way. It's a skill you have to have. You go in and you work those problems again and again and again and again and again. And you figure out what your weakness is, and you figure that out, and you turn that into a strength, okay? Because you know what's going to be on the test. I told you what's going to be on the test, okay? Oh, there's the force and acceleration graph. Man, I got to know that. And on the test, I'm going to ask you this. I'm going to give you that force and acceleration graph, and I'm going to say, hey, what's going to happen to that graph if I make the object mass bigger, or if I make the object's mass smaller? And again, you all did a worksheet on that. You did an entire thing. We laid it out. Here was the graph. Oh, it's a direct relationship. Oh, here's the linear function. Oh, A equals the slope times the force. You had that. Oh, here's an acceleration. What did you get from the force? Or here's the force. How do you get the acceleration? And then I said, hey, okay, what would happen to the slope if we made it more massive? So if you go back to that assignment, it's the one where it had like 3 graphs across the front of it on the front page. There was that one with force and acceleration. Go back and work that problem again. Start from scratch. Cover up your answers. Now, let me tell you how not to study for this test. Don't sit in your room on Monday night and lay out all your assignments and then have your AirPods in and you got your phone over here and you're watching TikTok videos and you got the TV on and mom and dad walk by. What are you doing? Oh, I'm studying for my physics test. Okay? No, you're not. Right? You cannot multitask. Okay? You're teenagers and you think you can't. No. Okay? Learning is an active process. Sit there and think these problems through. And you work them again and again and again. Make a flashcard. Make 6 flashcards. Oh, what are the units for distance? Oh, meters. Oh, velocity. Boom, meters per second. Acceleration, meters per second squared. Force. Oh, 2 options on force. Newtons or kilograms meters per second squared. Because unfortunately, if you don't know the units, you can't do dimensional analysis. And I promise you, you're going to have to do dimensional analysis. So I'm going to give you something like force equals m times v minus v naught over time. And I'm gonna say, hey, prove that this equation is valid. This is one of the things you can do. So I'm gonna be on the back side of the test, okay? I'm gonna give you something like this. Oh, okay. Now, you see that M. Is that M meters or is that M mass? Which one is it? There's a huge difference between the two. Mass. That's a mass. You see M as a variable, that's mass. What units are you going to put in there? Kilograms. Okay, so we got kilograms. Boom, there we go. I got my two velocities. Angel, what units is velocity measured in?
Meters per second.
So I'm going to have meters per second minus meters per second divided by seconds. Now, is meters per second minus meters per second equal to 0? Horrible. No. Stop. No. Okay? All that tells you is that you get meters per second out of it because it's the same units. So then you go, oh, that's kilograms, meters per second over seconds. Now, instead of dividing by seconds, what are you going to do? So this becomes kilograms, meters per second times 1 over seconds. And you get kilograms, meters per, that's what force is measured in. When I tell you to do dimensional analysis, this is what I expect to see. I expect to see things canceled out, to multiply by the reciprocal. That's what I expect to see. Okay, so here's what I've got. So this is just kind of a review, okay? It's not due, right? This is, if you can do this, you can kind of feel good about the test. I'm giving you the answers to it, okay? I'm giving you the answers. But here's what I would recommend. Don't read question number 1 and then look at me and go, oh yeah, I would have got that exact same answer. Number 2, oh yeah, Burkamp, you're on a roll, man. This is cool. You know what you do. No, okay? I would work this and not even breathe on that answer sheet, okay? I literally wouldn't even breathe on it. Work this whole thing. Treat it as the test. And then go to here and see how you did, okay? That's what I would recommend that you do. The problems that you get to this and you don't, man, I don't know how to do that. That's something that you need to work on. Now, there's going to be things that are on the test that are not on this review. Like the force and acceleration. Not on here, okay? Because that's on that other sheet that I've given you. But this is kind of like there's a conversion of kilometers per hour into meters per second. There's significant digit calculations, okay? There is conversions, that type of thing, okay? So that's what's going to be on here. Yes?
When we're doing the study guide or whatever, should we use our big dog sheet or should we try to go off?
No. You will have your big dog
Okay.
equation sheet on the test.
Okay.
You will always have that available to you on the test. Okay? So I'm going to hand this out. My concern is that you're going into a 3-day weekend. Okay? I'm telling you, if I were you all, don't wait until Tuesday or Monday night. Maybe hit on this stuff a little bit Saturday. Maybe it's definitely on Sunday. Okay, the Chiefs don't play until Monday night. Or Chiefs don't play at all this weekend. They have the bye week. So there's no excuse. Oh, I was watching the Chiefs games. No, you weren't. Okay? Don't throw that out at me. Okay? Chiefs don't play this weekend. All right? Okay. I'm done.